In today's class, we will discuss Module 3, Operational Amplifiers and its applications. So this is the schematic symbol for an operational amplifier. Operational amplifier is a high gain direct coupled differential amplifier which is used to amplify both AC and DC signals. The most commonly used operational amplifier is mu A741, where mu A indicates the company name Fairchild, and the saturation voltage for an operational amplifier ranges in between plus or minus 12 volts to plus or minus 18 volts. The name operational amplifier because it is used to perform the mathematical operations such as addition, subtraction, multiplication, division, differentiation, integration, etc. It consists of two input terminals. The negative terminal is called the inverting input terminal. The positive terminal is called the non-inverting terminal, and it has one output terminal V0 is equal to AV into VID, where AV is the voltage gain. It is defined as the ratio of output voltage to the input voltage, and VID is the differential voltage, which is defined as the difference between the input voltages applied to the input terminals of an operational amplifier. Coming to the operational amplifier pinout diagram, it consists of 8 pins. So let us take the pinout diagram. It consists of 8 pins. Pin number 1 is called the offset null. So offset is to nullify the output voltage. So without giving any input, there should not be any output. And pin number 2 is input terminal, that is inverting input. Pin number 3 is non-inverting input. Pin number 4 is supply voltage minus VCC. Pin number 5 is offset null. By connecting pin number 1 and 5, it is possible to make the output voltage 0, and pin number 6 is output. We are going to measure the output, and pin number 7 is plus VCC, and pin number 8 is no connection. Now, the next topic is coming to the block diagram of an operational amplifier. Basically, it consists of 4 blocks. The first one is input stage. Next is the intermediate stage. Next is buffer or level shifter. And the fourth stage is output stage. So as we have discussed, the operational amplifier has 2 input terminals and 1 output terminal. So the 2 input terminals are inverting and the non-inverting input. So the non-inverting input and the inverting input. So the input stage has the dual input balanced output differential amplifier. Intermediate stage as dual input unbalanced output differential amplifier. The buffer stage as the emitter follower using constant current source, constant using constant current source, and output stage as complementary symmetry push-pull amplifier. To handle the large amount of power. So basically, the block diagram of an op-amp consists of input stage, intermediate stage, level shifting, and the output stage. So input stage is a dual input, balanced output differential amplifier which amplifies the difference between the two input signals. This provides high input resistances or the impedance to avoid loading of the two input signals. This stage provides most of the voltage gain of the amplifiers. The second one is the intermediate stage. The intermediate stage is dual input unbalanced output differential amplifier. The output of the input stage drives the intermediate stage. This is another differential amplifier with dual input unbalanced output, which indicates it as a single-ended output. The function of the intermediate stage is to provide an additional voltage gain that is required. And the third stage is the buffer amplifier or the level shifting stage. Because of direct coupling, the DC level rises from stage to stage. This increase in DC level tends to shift the operating point of the active device used in the next stage. To bring down this DC voltage to zero, a level shifter used, which is usually an emitter follower circuit. An emitter follower circuit is one in which the output voltage follows the input voltage. This also acts as a buffer with a very large input resistance and very low output resistance. And the output stage is the function of the last output stage in the op-amp is to supply the load current and provides a low output impedance. And basically, the operational amplifier can be operated in the differential modes. One is the single-ended input, differential input, and the common mode input. So what is a single-ended input is, in this mode, the signal voltage is applied to the one input and the other input is grounded. And the second one is the differential input mode. In this mode, the double-ended differential mode, two opposite polarity signals are applied to the inputs. And the common mode operation is, in the common mode, two signal voltages of the same frequency and amplitude are applied to both inputs. They tend to cancel, resulting in a zero output voltage. Coming to the ideal characteristics of an operational amplifier. Important ideal op-amp characteristics. Ideal op-amp characteristics. First one, input resistance is very high. That is Ri is infinity. Second point, output resistance is very low. output resistance is very low. Third one, characteristics do not drift with respect to temperature. Characteristics do not drift with respect to temperature. Open loop gain is very high. So what is a open loop is if there is no feedback, it is called open loop. If there is a feedback, then it is called a closed loop configuration. Open loop gain is very high. That is AOL is infinity. And the next one, fifth one, zero input offset voltage. Zero input offset voltage, that is VIO, is 0. Next, zero input offset current. Zero input offset current, IIO, is 0. Next one is infinite bandwidth. What is the bandwidth? Range of frequencies over which the power of the circuit reduces to one half of its maximum value. It is infinite gain bandwidth product. What is the gain bandwidth product is the bandwidth of an op amp when the voltage gain is infinity. The next one is infinite CMRR. The CMRR is nothing but the common mode rejection ratio represented by rho, defined as the ratio of the differential gain to the common mode gain, and the unit is decibels. And the next one is infinite slew rate. Infinite slew rate. Higher the slew rate, better the performance. Next one is zero power supply rejection ratio or voltage supply rejection ratio. And the next property is when V1 is equal to V2, when V1 is equal to V2, the output voltage is 0, called the perfect balance. Called the perfect balance. So now let us consider the op amp parameters. Op amp parameters. First one, common mode rejection ratio CMRR. It is defined as the ratio of differential gain to the common mode gain, represented by rho. Rho is AD by AC. The unit is decibel. So what is the common mode gain is both the inputs of an operational amplifier is made common. This is V0, this is V1 and V2. And the differential gain is, it is the difference between the two voltages applied to the input terminals of an op amp. So this is VD. VD is nothing but it is the difference between the two voltages. The next one is slew rate. Higher the slew rate, better the performance. It is defined as the ratio of change in output voltage with respect to time. That is dV0 by dt. Slew rate indicates how fast the op amp responds to the changes in the input signal. If it takes more time to respond, then there will be a distortion. And the third one is input bias current. Input bias current. So what is input bias current is?
It is the average sum of the currents entering into the input terminals of an op-amp. And the next one is output offset voltage. Output offset voltage, VOO. The actual value of the output voltage when the inputs of an op-amp are zero is called the output offset voltage. So let us represent schematically when V1 is 0, V2 is 0. If the supply voltage is given, V0 is not equal to 0. The next one is input offset voltage. Input offset voltage. Input offset voltage, VIO. The input offset voltage is the voltage that must be applied between the two input terminals such that the output voltage becomes zero. So you can represent schematically. So this is VIO, the input difference between the two inputs. V0 is zero. The next one is input offset current. The input offset current represented by IIO, it is the difference between the currents entering into the input terminals of an operational amplifier. And the next one is input impedance. The input impedance is represented by ZIN. It is the equivalent resistance that can be measured at either the inverting or non-inverting terminal with other terminal connected to the ground. So schematically, we can represent like this. So this is the V1 input. This is also V2 input. This is ZI, and other terminal is connected to the ground. So this is Z0, the output impedance, and this is V0. And the next one is output impedance. Output impedance. Output impedance Z0. Output impedance Z0. It is the equivalent impedance that can be measured between the output terminal of an op-amp and the ground. And the next one is power supply rejection ratio, or also called as voltage supply rejection ratio. It is a measure of how effective the op-amp is in dealing with the variations in the supply voltage. That is, the change in op-amp's output offset voltage caused by the variations in the supply voltage. That is, it is mathematically given by delta V0 by delta Vs. Delta V0 is change in output voltage and delta Vs is change in the supply voltage. And the next one is 10th one, gain bandwidth product. So before going to the gain bandwidth product, so bandwidth is the range of frequencies over which the amplifier performance is satisfactory, called the bandwidth. And the gain bandwidth product is the bandwidth of an op-amp when the voltage gain is unity, is called the gain bandwidth product. So next topic, let us consider the virtual ground. Virtual ground concept. Virtual ground or virtual short. Virtual ground or virtual short. We know that ideally voltage gain of op-amp is infinity. AOL is infinity. But the voltage gain is defined as the ratio of output voltage by input voltage. That is V naught by VD. What is VD? Is the differential voltage. That is the difference between the voltages applied to the input terminals of an operational amplifier. So this is the schematic symbol of an operational amplifier. VD is nothing but it is the difference between the two voltages. This is minus and this is plus. If the voltage gain is infinity, AV is infinity, then V2 minus V1 is equal to 0, which implies that V2 will be equal to V1. This shows inverting input and non-inverting input terminal are at same potential. That is, inverting terminal appears to be same as the voltage at the non-inverting terminal. And the zero input current. Ideally, the input impedance is very high. Since the op-amp has a very high input impedance, it does not allow any current to pass through it. So therefore, whatever the current flows through the input, the same current flows through the feedback resistance.